Okay, so good afternoon, ladies and gentlemen, and thank you for tuning in to another Risk Institute online session. Today, we're fortunate to have with us Dr. Craig Poku, a researcher from the University of York's Wolfson Atmospheric Chemistry Laboratories, who will talk to us about his research on aerosols to understand nocturnal radiation fog. Increasing understanding of aerosol impacts on fog will lead to improved fog forecasts and decreased risks associated with human health and activity, so it's rather important. And the presentation will be around 45 minutes and 20 minutes of questions and answers. So please could you make sure your mic's muted and post your questions in the chat or raise your hand after the talk and I'll select them on behalf of our speaker. So firstly, I'll just introduce our speaker, Dr. Craig Poku. He is a trained mathematician turned atmospheric scientist. In recent years, he has focused on addressing challenging societal issues. And following a year in local government, he went on to complete a PhD in atmospheric sciences from the University of Leeds, which specialized in investigating fog microphysics. He's now working at the Wolfson Atmospheric Chemistry Laboratories, where he's investigating how we can apply new and novel analytical techniques to air quality monitoring sites. So without further ado, Craig, if you'd like to unmute your microphone and begin your talk. Thank you.
Firstly, thank you, Francis, for inviting me to do this talk. And secondly, hello, everybody. So as Francis has mentioned, my name is Dr. Craig Poku. I am a mathematician turned atmospheric scientist, and I currently work at the University of York. However, today's talk is actually going to be on some of the work that I did prior to my current post, which was at the University of Leeds, and that was looking at aerosol impacts in nocturnal radiation fog. And today's talk, I'm going to be mostly talking about uncertainties and why uncertainties are very difficult to try and quantify, especially in the context of aerosol. So what was the motivation for studying fog? Fog is a low-lying cloud that results in your surface visibility decreasing. And the problem with fog is that there are multiple physical processes that make the interactions very difficult to poorly represent in models, and hence making it very difficult to forecast. And the reason as to why these poor forecasts are really important is because if you think about having a poor forecast, they have impacts on the economy, travel and human health and safety. And an example being that in 2013, there was a major crash that happened in Sheffield, South East England, resulting in 130 crashes and 12 injured due to sudden onset of thick fog. Now, there have been a number of recent studies that have actually highlighted the importance of aerosol in terms of how it changes the fog's macrophysical and microphysical properties. And so the key objective of this work, of this first part of this talk, is actually looking at the impact of aerosol fog interactions during the fog evolution and its transition to a well-mixed layer after formation. Now, I've kind of mentioned aerosol a few times in the first couple of minutes of this talk, and I'm going to just talk about why are aerosols key to our understanding of fog formation. Now, aerosols are like these really small, tiny particles that are suspended within the air, and they can range from particulate matter, which is important for human health from the perspective of air quality, to sea salt. And they can come in different shapes and sizes, and they've got different sets of properties. Now, here is a very idealized scenario. We've got three aerosol here. We've got aerosol A, B, and C. And in this particular situation, we're actually going to then simulate the scenario that we're having an increase in relative humidity. So in this case, the atmosphere is approaching saturation. And when I think of saturation, you could think of it as if you've got a sponge, you put it under a tap. The amount of water that that sponge can hold, that means that it's approaching saturation. As the atmosphere approaches saturation, it then goes into state of instability. And what we find is that these water particles, or these water vapor particles that we're seeing around in the atmosphere, want to actually then go, well, I'm in an unstable scenario. What can I do to basically reduce that instability? And so then we've then got what's known as condensation. Now, the question is, of all of these aerosols, which ones are going to result in the best form of condensation? If we look at aerosol A and aerosol B, we notice here that aerosol A has a higher solubility despite the fact that it's actually the same size as aerosol B. And because of this, the water vapor will then result in then actually more likely wanting to condense on aerosol A as opposed to aerosol B. However, if you look at aerosol A and aerosol C, despite the fact that aerosol A and aerosol C have the same solubility, because aerosol A is of a bigger size, this then means that the energy required for you to then have condensation occur will be less, and hence aerosol A will then result in you then actually having condensation occur. So in this particular instance, what we're dealing with here are soluble aerosol, and this is going to be the focus of my talk. But one thing to note here is that aerosols that are larger in size and more soluble are more likely to become the nuclei of cloud droplets, or in this case, activation. And this is quite important when it comes to trying to model these uncertainties. So how does the diagram that I've just related to before link back to aerosol-fog interactions? Fog has several processes that form, and what I'm going to do is I'm going to see if I can try and get this to work now. One thing we note here is that fog forms through a process known as radiative cooling. So radiative cooling is the release of heat through the Earth's surface during nighttime, and what you'll find is that during this heat release, this area of the atmosphere is going to start cooling. Now, as you start cooling, you then result in you then actually then go to a stage of saturation. And then because of the saturation and then eventual supersaturation, what you'll find is that these water vapor particles will then want to then condense onto these aerosols. So in this particular scenario, the aerosol that we're only dealing with are cloud condensation nuclei. Now, what you'll then find is that if you've got enough of these aerosol forming fog droplets, you then have the beginning of a fog layer. And you've got two competing processes occurring here. You've got fog droplets that are forming and then they're sedimented to the ground, but then you've also got fog droplets also continuously being formed within this process. And what you'll find is that if you've got enough fog droplets within your fog layer, you will then find that the cooling that happens at the top of the cloud, so in this case, the development stage, will be greater than what you're finding occurring at the surface. This will then result in you then having what's known as a well-mixed layer or convective layer. And the question is that where does aerosols role play between the formation to development stage? And the more important question is, are we actually capturing the physics correctly? And more importantly, the model uncertainties. So in order to try and test this hypothesis, what my PhD focused on was simulating a case that was known as IOP1. So IOP1 is IP1 is based on a case study from a recent fog study that happened in the southeast of England between the winters of 2014 to 2015. And is based in Bedford, which is in this really nice circle here. I can tell you that Bedford is a brilliant place to be. Now, for this particular instance, or this particular case for IOP1, the reason why this has been a really well-studied case is because it's been known as what's known as a stable case, i.e. it never reached the well-mixed stage. And the way in which I'm going to be simulating this case is through a model known as MONK, or the Met-Office-NERC model. So MONK is a LES model that can resolve atmospheric flows at different scales. And the reason as to why we are using MONK as opposed to something that is more forecasting related is due to the fact that MONK allows us to do idealized studies. So actually go, okay, if we wanted to try and fix all of our variables in terms of atmospheric processes, but focus on aerosol, you can use something like an LES model. One thing to note here, though, is that despite the fact that the focus of this work is on aerosol, one thing to note is that we had no measurement because the measurement, the instrumentation that was measuring aerosol actually broke halfway through. And so all of the aerosol measurements that I'm going to be discussing in this particular case are idealized. Now, because I was really focused on sort of understanding the microphysics, MONK was coupled with a scheme known as the Cloud Aerosol Interactive Microphysics Scheme, or a bulk microphysics scheme in small terms. And the reason why this is really useful is because not only does it account for things such as aerosol formation, to cloud droplet formation, to sedimentation, but it then means that this particular model, if we can see that actually this particular bit of physics is not being correctly implemented, then we can then look at how this relates back to forecasting. I'm going to mention this once. The aerosol activation scheme in question here was called Abdul-Razak. The reason I'm mentioning it is because part of my work was actually really understanding whether aerosol activation or cloud droplet formation was being represented properly, and this is the default scheme that's used in the forecasting model at the moment. And again, as I mentioned, it's a method to account for fog droplet formation. And the more important question is this scheme suitable for UK fog forecasting? Because if it's not, then what are our alternatives? So here is an example of some of my very early work, which I then went, okay, so let's assume that everything is perfect and we were trying to simulate this case. Would we be able to capture this transition to a slightly thicker fog? So this bit where it goes from a slightly higher visibility to something where it hits the fog stage and it's relatively stable. Now, one thing to note here is that the purple line, which is our control simulation, is actually dropping down in visibility too quickly. However, it actually captures the fog at a slightly later stage a bit better. Likewise, one thing to also note, though, is that we actually see that the red line, so if we were to reduce our aerosol, actually there results in a slightly slower transition. And so really what we want is a scheme to capture something in the middle here. And you may be going, why are we having a decrease in aerosol resulting in this slow transition? If you've got less aerosol within the atmosphere, then less aerosol will then be able to then activate, which then results in you then having that feedback loop of a thicker cloud layer reducing. Likewise, if you've got more aerosol in the atmosphere, then the competition of water vapor then increases, which then results in you then end up having a thicker layer, as we basically see here. So what this particular plot, and I really like it because actually it's a really nice demonstration, it basically highlights the fact that it suggests that the current scheme that's used in the UK forecasting system is actually incorrect. And it motivated some of my later work, which was then, okay, how could we then potentially improve the physical representation? Now, I've kind of gone into this term known as aerosol activation a couple of times, and I'm aware that as somebody who was a mathematician who didn't know what atmospheric sciences was prior to starting the PhD, just jumping into aerosol activation is very difficult. So rather than me trying to explain like the physics straight away, I'm going to explain it in the context of a sink and why this is really key when it comes to fog. So I discussed how fog formed because of radiative cooling, and this is what you can see as a source of supersaturation. So in the case of adiabatic clouds, this is the case of convection, but more specifically to the work that we've got here, this is through radiative cooling. But what you'll then find is then as you then increase your relative humidity, you're then having a source of supersaturation, but then you then basically then go to a state of instability. Now, because you're in an unstable environment, you're then going, oh gosh, these water vapor particles are like, oh my gosh, what do? I need to basically reduce this instability because it's not a nice place to be. And so this is when condensation happens. But because you're having condensation, you're removing water vapor from the atmosphere, and then that decreases your relative humidity. And so the difference between the increase in supersaturation due to cooling minus the decrease in supersaturation due to condensation leads to the total number of droplets being formed. Now, why is this a problem for fog, you may ask? Well, the first thing is that Abdul-Razak and Gard, the scheme that I spoke about, is derived on this idea of adiabatic ascent. And so therefore you're having a physical system try to represent another physical system, but neither of them are actually corresponding. Radiative cooling is very different to convection. The second thing as well is that a lot of forecasting schemes implement this updraft velocity threshold. So this means that the reason why they do this is because in a lot of schemes, trying to represent very low updrafts results in numerical instabilities, as they've implemented this threshold. The problem with this threshold, though, is that this threshold was actually derived in the 90s, and computing power has changed so much from then till now. So maybe this threshold is not actually applicable to the work that we're doing. The other thing also to note here is that radiative cooling is a much slower cooling form. So generally speaking, you have 1 Kelvin per hour will result in fog forming in the UK. This threshold, as you can see, is resulting in an equivalent of 3.51 Kelvin per hour. And generally speaking, adiabatic ascent has a much stronger cooling rate. So what you're then finding is then you're potentially having an overestimation in aerosol activation. And so this was sort of then going, could we potentially improve this in models? And so the next bit of my work then looked at then going, okay, well, why don't we then try to take the hypothetical framework of what's happening in aerosol activation and incorporate the physics that's happening in fog. So in this case, I incorporated a non-adiabatic cooling source, otherwise known as radiator cooling, into a model that's known as shipway. And the reason why we moved from shipway and moved away from Gun is because it performed better in low CCN or clean aerosol regimes, therefore being suitable for this particular case study that we're looking at. This is a more mathematical framework of the schematic that I showed. So we see that the change in supersaturation is equivalent to the increase in saturation due to adiabatic ascent minus condensation. The thing to note here is that shipway was developed to focus on convective clouds. So this term here is not potentially applicable, plus it also incorporates this WMIN that I mentioned before. So what my work did, which was known as the SMOD scheme, was to also incorporate this non-adiabatic cooling term, as well as also removing the need for a minimum threshold. And this is a more physical representation of what's happening in fog, but also the main advantage of using a dual scheme like this is that it could also be used for convective clouds. Therefore, it basically covers a much wider cloud regime. So here is an example of when I've applied this scheme that we had. So here we've got case A. So this was based on using Gun, and we see here that because our cloud droplet number or aerosol activation scheme is being calculated too strongly, this then means that you will then having too much cooling happening at the top of the cloud, and we then start to have a well-mixed layer. However, what you find is that if you then use SMOD, so the new shipway scheme that has the non-adiabatic term, we find that because our CDNC or our droplet number is essentially lower, you then find that this well-mixed layer is becoming less. And the reason as to why this is quite important is because I'm not saying that this new scheme fixes everything. However, it was leading to a solution or a potential solution that was a bit more suitable for fog. But the main question then I then went was, and this is probably going through the review process, was, well, is this the end? Does this mean that we fixed all the fog problems? So let's go back to our schematic or our diagram. We notice here that we do have this well-mixed layer that is forming less. However, what I haven't shown you here is that going from A to B did not account for a lot of model uncertainties. And this is something I'm going to discuss really briefly. So obviously I mentioned that we went from A to B, but it doesn't actually incorporate that there are many variables that actually got picked up in this. The first one is this important term known as the effective radius. So a key aspect is that if you've got a population of cloud droplets, they will then result in long wave radiation being emitted from its surface. And the more droplets that you have in the atmosphere, the higher this long wave term will basically be. And this is what basically a summed up version of what the effective radius is. SMOD, when I initially implemented it, didn't actually account for the changes in effective radius with droplet number, which meant that actually what we were finding is that SMOD was performing worse. And this is one thing that also allowed us to then go, okay, these are some other aspects of the model that we need to take into account. And this is why cloud uncertainties are very high in terms of research. The second one is that the minimum threshold removal with shipway initially performed better. And this is actually due to the fact that the effective radius wasn't being taken into account. And I kind of mentioned this because, again, it also goes back to this whole idea of really ensuring that you understand all the bits of the model. And the final thing as well is that we only tested this case in cloud aerosol regimes. So when you look at this conclusion, you go, okay, well, this fixes fog for all aerosol regimes. But actually, in some of my later bits of work, you'll find that actually maybe applying something like this doesn't necessarily count. So the latter bit of my talk is actually going to be talking about my work that I did when I looked at fog in India. So all of the cases that we looked at were sort of like, idealized cases of fog in the UK. But the reason why fog in Delhi is really interesting is actually it strongly links to air pollution. So one thing to really know is that when people talk about fog and you talk about fog with people who live within Delhi, their mindset's completely different, because usually what you're finding is that you're then dealing with really bad air pollution episodes. So there were a few questions that came from this bit of work. Was one, how do aerosol impacts potentially differ in a more polluted regime? Two, could this potentially be used to motivate future air quality policy? So we could see that there was a very strong link between, say, fog formation and like fog and aerosol, not aerosol, air quality episodes, could we potentially use one to mitigate the other? But then also another question would be is where should fog resources or forecasting resources be focused on? And the reason I mentioned this is because you can't just go, well, we've got our system, it works, and then afterwards we're just going to just jump it into something else, because not only is the meteorology completely different, but also it doesn't take into account that actually there are people who are already looking at fog forecasting in India. So what we should be doing as researchers is actually go, how can we reallocate our resources, or maybe actually go put some more effort into this bit of research as opposed to this bit of research. And we're going to kind of explain how this last question was done through some of the work that we did. So before we could actually go, okay, which idealized cases we wanted to look at, we needed to, actually understand what we needed to do actually is actually then go, okay, well, where can we basically, before we were able to basically go which cases we could potentially simulate, we needed to actually understand where we needed to allocate our resources, and more importantly, whether the cases that we were going to pick would be of interest. And so in order for us to be able to do this, we need to actually see with the cases and the simulation data that they had, which ones would we basically focus on. And so in order for me to sort of explain this, what we're going to do is actually go through the schematic. So here we have 6 fog cases, and these 6 fog cases all have different properties, but the main question here was which ones would take priority and why. So most times whenever we come to looking at fog, we always go, okay, right, well, a fog case by definition needs to meet a particular threshold or a visibility threshold. So in this case, 4 cases for this particular example met the 1 kilometer threshold, and so therefore we could bring it down. The next part would be that fog cases can either be known as advection or radiation fog. The reason why this is important is because a lot of what I've been doing is radiation fog, so that will be easily translatable. And then what we see here is that for the cases that we basically were allocated, 3 of them basically were, 3 of these were radiation fog cases. 1 of them was an advection fog case. We brought it down and we could see that actually for the cases that we initially had, more of them were radiation fog cases as opposed to advection fog cases. So that would have been the ideal scenario. We were able to go, okay, most of the cases that we got were radiation fog cases. I was got experience in radiation fog. We can easily translate that information over. What we ended up finding, however, was this is where aerosol becomes very uncertain in this particular regime. So we then went, okay, well, we actually found that we then had a bunch of cases that all met the initial threshold. So this particular case, we found that all 6 of our cases met that threshold. We then said, okay, right, well, of the physics that we can see, which ones could be separated into advection and radiation fog cases. So we then split those in. But what we actually noted here is that we found that we ended up finding that we had a number of cases that were considered as fog. However, they didn't meet all of the meteorological variations or the meteorological conditions that we are known as fog scientists. And there could be several reasons for this. The reason being was that 1, we didn't take into consideration potential physical processes that impact fog. The second one is that there were the uses of thresholds. So of course I mentioned that we had 1 threshold for visibility, but actually for Delhi, we may have found that this actually really differed. What we ended up finding is that actually it was the local environment and these aerosol uncertainties. So what you will find is that if you go into really high polluted regimes, what you're dealing with is not necessarily fog, but what's known as the aerosol optical depth. And the reason why the aerosol optical depth is important is because the more aerosol that you have within an atmosphere, the more light that will be scattered, and therefore you have a very similar drop in visibility. And this is something that we're writing currently in a paper at the moment. So this meant that when it came to then trying to then pick a case, what we found here is that in all of the previous work that I did prior to this particular piece, so just for context, this was an idealized case of a fog IOP that was observed in Delhi. What we note here is that even though we do actually have a drop in visibility, all of the models don't pick up fog until you basically go into what's known as like the optical depth stage, or like a really deep fog. And the reason as to why we're having all of this is because of the aerosol optical depth. And this is something that we ended up realizing and ended up having to change our approach when it came to actually then go, okay, how do we account for more fog simulations? But one thing to also note as well, and this is actually quite an interesting case, is that the general consensus is that the more aerosol that you have within the atmosphere, the more condensation that will occur, which then results in you then having more fog. What we ended up finding here is that the more aerosol that we had in the atmosphere, the less fog actually then occurred. And this is what we notice here, that as we increase our aerosol number, we actually have a decrease in visibility. This mostly is down to the fact that because the water competition, the water vapor competition is so great, what you're then finding is that actually you may end up finding that condensation is then basically being prohibited. So you're in an aerosol repressed regime. So what this work showed us is, one, aerosol uncertainty is a pain, but two, and more importantly, we need to basically take our way in which we look at fog modeling on a more case-by-case basis and actually be more careful with regards to, like, you know, the physical representation as well as potential aerosol uncertainties. So to kind of summarize this talk, there are some key points, and of course, I'm really open to questions from everybody. Using an aerosol activation scheme to divide for convective clouds is not suitable when it comes to looking at fog. And one thing to also note here is that we see that a more physical-based representation of aerosol activation can slow down the transition due to a more appropriate droplet number being calculated. However, you also need to be assuming that you've got the right level of uncertainties, or more importantly, uncertainties are being taken into consideration. However, more specifically today, one thing we noted is that all of the fog cases that we tried to simulate using Monk did not form the model until the meteorological condition of a relative humidity of 100% was met. And this is really important because it then means that if we are going to try and simulate fog, or more importantly, simulate aerosol impacts in terms of fog forecasting, it may not just be as simple as going, oh, we need to look at, say, the meteorology, but it could also be that we need to look at, say, for example, what is the predicted air quality for that particular regime going to be for that particular day, and could we do that in conjunction with fog forecasts? And the final bit is that research is currently ongoing to develop Kazim, so the model that I did most of this work with, and more importantly, how it can take into account different aerosol processes. But hopefully, fingers crossed, if the development's going the right way, then it should be able to improve our capabilities for operational forecasting. And with that in mind, thank you very much for listening to this talk. I've left my email and Twitter details on the handle, and I've also left some papers that I refer to in this talk. And one thing to note now is that a lot of the work that I now do is no longer in fog, but it's actually in air quality, and more importantly, how we can use machine learning to improve our scientific insight within air quality. So there is a lot of transferable skills from my previous work to what I do now, but again, I'm open to any questions. So again, thank you very much.
Thanks so much, Craig, for your talk. That was really really intriguing. And I have one question to get the ball rolling before I open up to the audience. I was wondering whether you could tell us a little bit more about the risks that fog poses on, say, equipment or machines or human health, in fact, because I know that you kind of brushed over it a little bit, saying it has kind of risks involved, but do you know what some of the specifics are with regards to, say, human health?
So from a human health perspective, one thing to know is that for fog to form, you need to have aerosol. And depending on the size of the aerosol, they can be really good in terms of acting as cloud condensation nuclei. However, you may also find that if you breathe some of this aerosol in, you can not only have impacts on both your cardiovascular and your respiratory circulate. Also, my brain just went, give me a sec, I'm back now.
No problem.
Basically, it can have impacts both on, like, your cardiovascular as well as your respiratory systems. And that's mostly from an aerosol perspective, but more specific to fog, if you are dealing with an environment such as Delhi, you can actually have what are known as secondary organic aerosol forming. So because you've got such high humidity within the atmosphere, what you'll then find is that aerosol that are in the gaseous phase will then basically then begin to form, and they are known as what are known as volatile organic compounds, or like VOCs. These have been shown to be very harmful in terms of human health. And so from a air quality perspective, this is the reason as why fog has basically gained a lot of attention, because what you'll find is that actually what we may potentially have in the UK is that if we've got really poor air quality episodes coinciding with fog, actually the fog then results in you then having a much worse air quality episode, and they kind of working hand in hand. So that's one example. But mostly for a very long time, the main focus was not so much on air quality, but it was also more related to drops in visibility. So if you, for example, found that you had onset fog that wasn't predicted, then that then means that you could potentially have a potential car pile up. But again, that is now happening less and less because the other model uncertainties are being addressed.
Okay, fantastic. Yeah, so if you see fog in Delhi, you should almost definitely run away.
Yeah.
Go to a different city, yeah?
Yes, definitely.
Okay, thanks. Does anyone else have any questions from the audience?
So you never use the word smog. Is that because it's old-fashioned or because it's too specific? What do you call these in general? Because they're not just fogs, right? They're sort of contaminated fogs in a sense. They're not natural.
So in the case of Delhi, what we will tend to do, so we use smog still, but that term is being used less and less, mostly because when people think of smog, there's a very negative connotation. What we tend to do is that we usually say it's a poor air quality episode. So in the UK, we tend to usually get them around bonfire night, for example, where you will find that because we're having so many pollutants being thrown into the atmosphere, if you do, for example, have a very clear night, then you will then start to have haze beginning to form, or in most cases, smog. The reason as to why we try to tend to avoid using smog is because when people think of smog, they think of those really horrible movies where people are all going to die. And that's something that we try to avoid in terms of scaring people.
Really, that's amazing.
Yes.
Yeah, that's rather surprising. And I have another question as well, based on the graphs that you showed in your slides. I think it was you had the 3 lines trying to match the observation of fog.
Yeah.
You were trying to predict. And I was wondering, you said that you tried to incorporate some uncertainty into it, and I noticed that the uncertainty kind of didn't match the massive highs and the massive lows that were fluctuating. And what other uncertainty techniques you might have considered to be able to try and compensate for that, the mismatch there, if you've considered, say, like probability bounds or Monte Carlo and such.
When I did this bit of work, the way that I sort of looked at matching those uncertainties was looking at, so for example, what was the model's maximum and the model's minimum, and then afterwards I then calculated that for every grid box. Now that I've got a much better understanding of uncertainty, one thing that I would have potentially done is look at maybe if we knew what the mean visibility was, what are the different standard deviations per point, for example. Mostly because then we can then of course look at, for example, visibility as a distribution. The only problem with doing uncertainty like that is that there's the assumption that your visibility has to meet a particular Gaussian distribution or uniform distribution, which may not necessarily occur within the observations. And because we didn't have any observations to begin with, trying to guesstimate a distribution of aerosol when you had no aerosol to begin with was very difficult. One thing to note though is that when it came to actually looking at if we were to look at, for example, the changes in droplet distribution, it would be easier for us to be able to do that assumption because we did have some droplet measurements. And something that I didn't show here was, in order for me to do a number of the simulations that I worked on, I then looked at saying, okay, well, if we have a potential distribution of, say, a log normal distribution of cloud droplets, and we don't know what our different shape parameters were, then how could that then potentially then mean that we can then model that uncertainty a bit better? That wasn't really the focus of my final bit of the PhD, but that was something that I would have wanted to have done had I had the details to do it.
Yeah, absolutely. Thank you. Thank you very much. Sorry,
So,
were you about to say something, Scott?
well, I mean, I've had some distractions earlier in the talk. Maybe I missed it, but I don't really understand how you did the uncertainty, or how you incorporated the uncertainty into the model. So maybe could you tell me in maybe mathematical terms, what are you doing with respect to the uncertainty? So talking about, I mean, the equation you drew, presumably that would be
just so which uncertainty are we talking about?
Well,
this
yeah,
one?
that's what I'm particularly curious about.
Okay.
I mean, so what we're seeing in the colored lines, well, the non-cyan lines, I guess, are the prediction, the different approaches giving different predictions, right? And you have the uncertainty bars, or the uncertainty cones, I guess, there. So we think of the different colors as different models, the cyan being the raw data, I guess. Is that right?
Yeah.
And so what makes the breadth there? You said something about in the cells. So how do you mimic the uncertainty?
Okay, this is kind of the reason why I'd wish we did this in person, because I would have just gotten a whiteboard.
Right.
So the way in which the visibility is calculated within the model is that it's done as a ratio of liquid water content to droplet number. So there's an equation, I think it's like 1 divided by this product to the power of a factor of C. Now, the way in which the model then so that is the way in which you calculate visibility. But the way in which I kind of calculated this uncertainty, as we can see here, is that because you've got turbulence that is also having an impact on your liquid water content, then I was then able to then go, okay, so what is your maximum liquid water and what's your minimum liquid water per grid box? And then what I then did is then what we're seeing here in terms of the uncertainty is what is the maximum liquid water content for a given grid box at that very specific time step. And then that's what this difference was. And then likewise what the minimum was. I'm aware that upon reflection, and this is probably from now being in the work that I'm doing, that doing this as an uncertainty doesn't necessarily capture what is the uncertainty within this particular set of simulations. And I think upon reflection and now having a lot more information in terms of uncertainty, I would have gone about this completely differently. Only because I believe that there were aspects within the way in which I did this maximum and minimum that I didn't capture some of the aerosol uncertainty as an example.
Right. So the blue, which I guess you're calling OBS, I guess. So that's, I guess we might call that a trajectory, in that it's measured at a continuous time, or continuously over time at some site, right? So when you say grid, you're talking about a grid in time?
Yeah.
Okay. So that trajectory, of course, is very wiggly, and all of your predictions are sort of much more smooth. And so do they represent the mean of trajectories, or are they sort of the mean simulation?
Yeah, so the simulation, so T control, T double CNN and T half CNN, these are all the mean trajectories.
Mean.
To note here is that with the observations and in the way in which the observations was calculated for the visibility is that it was one site in what they thought was a representative of the entire site. But the problem with fog is that because fog in the very early stages can be quite patchy, what you're then finding is then you'll then find that as the fog is moving over that observation site, you're then going from, oh, there's some fog, to there is no fog, to there is a bit more fog, to then there's no fog.
Okay.
So really, in an ideal scenario, what you want to do is you're going to try and match what's happening with the observations to the model. You kind of also want to then have, say, a set of instruments across that site, which will then calculate visibility at different points, and then you then do your uncertainties on that.
Right.
Unfortunately, it didn't have that information. This was the
Right,
best I
okay.
had in terms
So,
of observations.
I apologize if you can hear the siren. We're all going to die. I think
Oh,
the
no.
building's on fire. I'm not sure if you can even hear that. But okay, so that's really helpful. So, but it does seem that, I mean, your explanation for why it's sort of bouncy in the beginning is really sensible. But then even in the sort of in that second domain, it's clearly also stochastic there too. And I'm
Yeah.
guess, is it a similar reason because the fog is uneven, I guess is the explanation?
It's to do with the fact that the fog isn't well mixed. So because the fog is still, so if I go back to this stage, this is a very idealized scenario for what we're
Right.
seeing here. Because the fog was still in this formation stage, what you're finding is that you're still having these weird, like kind of like patchy stages.
Right.
It's the only time that you find in observations that it becomes a lot more smooth is once it becomes well mixed, because then you're then having a more homogeneous layer then begin to form.
Can that actually happen? Because if it's well mixed, it might just be blown away, right?
It does happen in some cases within the UK. It's
Okay.
more common when you're dealing with higher aerosol regime. So if we go back to, let me find it, to this plot, for example, the observations here, we notice here that it's a lot more smooth. And that's due to the fact that in this particular case, what we found is that the fog was a lot more well mixed. However, again, there is a lot of uncertainty with the terms of how this was probably calculated as well. But we find that in the UK, this is why I'm just going back through the slides. Going back to the UK, we find that we do actually have a lot of more cases that look a bit more like this.
Right. And I suppose actually maybe, well, I guess those are pretty long. It's an hour between each tip, right? So, I mean, I guess in terms of hazards, road hazards of visibility, maybe you do kind of care about the stochasticity then.
Yeah, because
the peaks at least.
Yeah, and this is something that is quite interesting from an airport forecasting perspective, because and I really only appreciated this when actually I was coming back from Cape Town. So I went to Cape Town a few years ago for a holiday, and it was winter, which was their fog season. And my plane, funnily enough, this was about 3 weeks before I submitted my thesis, was delayed due to fog. Now, what was really interesting though is that they did allow for the plane to then eventually fly off to Johannesburg, but it was only once they knew that that spike was potentially going to be slightly higher. So for us, when it comes to, for example, looking at forecasting, the more important thing is, would we have potentially seen this potential spike had we had a better form of aerosol processes? The one thing to also note here as well, and this is something that I did look into in my PhD, however, I didn't put this into the talk because it was that bit of research that just never got finished in the end, was one thing is that a lot of the models don't account for what's known as nucleation scavenging. So nucleation scavenging is the removal of aerosol due to different processes. So in this case, the process would be condensation. And one thing to note is that when I did turn nucleation scavenging on in these simulations, we did find that we did get this sort of spike happening in visibility. However, the way in which the scheme was designed, because it was designed for adiabatic clouds, it meant that it was removing too much aerosol too quickly. And that was another thing that in terms of model uncertainty that I was like, okay, this could be something that could be interesting, but I just didn't have time to look into it basically.
Right.
Yeah. I thought it would be worth mentioning because this smooth line just feels too idealistic.
Right. So obviously you wouldn't want probably to simulate I mean, it would be nonsensical to try to simulate the individual things, but theoretically, I guess you could simulate the variance.
Yeah.
And maybe predict a band around that would include all those wiggles, I guess.
Yeah, that is definitely something that I know there are people in my old research group that are looking into. I wouldn't be able to answer that question though, because that was something that I didn't look into in terms of detail. Yeah.
Okay. Thanks. Sorry to monopolize.
So that's absolutely fine. I recently had some of my research published a few months ago. And so I had to think about these questions that you're asking me in a bit more detail. So hence why I can now go, this is probably what's happening.
Right. Yeah,
Yeah, thanks.
More people asking about the uncertainty, aren't they?
Yeah, thanks. I just a follow-up question onto that, if you don't mind spending a little bit more time. What would the kind of ideal scenario of observing multiple patches look like then, if you were going to kind of collate that information together, in terms of you have one observation point and the fog passes onto them and creates these kind of gaps. That's why it goes up and down. But if you were going to combine them both, I'm trying to think about how one might present that in the data in one graph. Would you have them as different lines or a kind of a larger bandwidth?
I think what I would have probably done is, if we had that as data, I would probably say, for example, have this blue line. I'd probably have, say, this blue line, have all the observations of this humidity for that particular period. And then afterwards, then I would then go, okay, right, so what is your mean, your maximum, your minimum, your median? I would literally just do the statistics on what's happening for each one of these points. So if you imagine here that we've got all of our observations, but rather than these being model simulations, they're all observations, then we then go, okay, well, we've got 4 points. So we know what the maximum minimum are. We can work out what the mean is. We can work out what the standard deviation from the mean is given those sets of data. So you can then do that for each one of the time steps. And I think what I would have done is I would have presented that data in conjunction with, say, this. And the reason as to why I think that is a neater way of going about it is because it's also highlighting the fact that you can't just have one model capture absolutely everything. The other thing to also note here as well is that the way in which the model was set up, it was set up as a grid box in the horizontal, and you've then got vertical grid boxes. But you've only got 1 point for your observation. So because of that, mathematically, you're looking at 2 very different systems. So if you have that appreciation of, okay, well, this is what I have for observations, this is what I have for the model, and you can at least then hypothetically say, this is what I would have done in a different scenario, then that's how I would go about it.
Okay.
Yes.
Yeah, no, that's really, really interesting. Thank you. Cheers. Any final questions before we wrap up? Vladimir, maybe? If not, then I'd like to thank our speaker again. Okay, no problem. So thank you very much, Dr. Craig Poku, again for your talk. And hopefully next time we'll be able to receive you in person or have an in-person event instead. So thank you again for your time. And it was a real pleasure to hear a little bit more about your research.
Excellent, thank you so much.
Thanks. Okay, bye.
Bye.